Without further ado, let us dive into the world of moles and volumes. Here we're going to face calculation after calculation after calculation. Now, along with the video of this PowerPoint, what you will find is there are videos of those calculations that sit separately in the playlist. So if there's not enough in this to understand the content, go have a look at those as well. Now, before we begin, we have to talk about the units of volume. You see, a liquid volume would be measured in litres or millilitres. That's the standard way. But with a litre, 1 litre actually has a equivalence on the metre scale. So if you remember that volume is length times width times height, and that all of these are measured in metres, then technically something in metres cubed would also be a valid unit of volume. So what is the connection between a litre and the metres cubed scale? Well, it's actually the decimetre, which is 10 centimetres by 10 centimetres by 10 centimetres, a 10 centimetre cube. That is 1 litre. And that's really handy because there are 1,000 of those decimeters cubed in a metres cubed, and indeed there's 1,000 centimetres cubed in a decimetre cubed. So it sits on the middle of the scale. It means that the 1 millilitre graduations on our measuring cylinders and beakers represent 1 centimetre cubed. And so 20 millilitres is 20 centimetres cubed. Now, the decimetre cubed is the unit that we are going to need to have for most of our calculations. But because so many volumes are measured in millilitres, we will occasionally give a version of the calculation that has been adjusted to accept centimetres cubed, but I'll tell you when we're at one of those. Now let's think about what we put into that volume. You see, we could put a certain number of moles into that space, and actually that'd be quite interesting. If I knew how many moles I had in a certain volume, then what we'd actually get is a new quantity, a quantity that we would call concentration. Now, you might at earlier points have looked at density as the amount of mass in a unit volume. Well, here we go the number of moles in a unit volume, and that is called concentration. The units for it are moles per decimetre cubed. In index notation, that's mol dm to the -3. Now, because the number of moles divided by the volume equals the concentration, sometimes it might be worthwhile writing it out as the number of moles is equal to the concentration times the volume. And here we have that first problem, the conversion between decimetre cubed and centimetres cubed. For you see, volume is normally measured in centimetres cubed, with the graduations on our measuring cylinder being millilitres and all. And this formula, if concentration is in moles per decimetre cubed, then this formula is going to get stuck. We have to convert those centimetres cubed first into decimetres cubed before we put it into this formula. So look at how we do it. If we take the volume in centimetres cubed that we've just read off the measuring cylinder, divide it by 1,000, that puts it into decimetres cubed, which is the correct format for the volume in this formula. Then if we multiply that by the concentration in moles per decimetre cubed, it would actually tell us the number of moles. So remember, if you're going to work with concentration, and we are taking measurements in centimetres cubed or millilitres, we have to divide those readings by 1,000. It isn't always convenient to have concentration measured in moles per decimetre cubed. In terms of convenience, if you were physically trying to make up this chemical, then you would need to know what mass of the solid to add to what volume of the liquid. And then what you'd be making is a standard solution. To do that, you might be trying to aim for a certain concentration in moles per decimetre cubed, but you'd need to work out what mass would be needed to create a concentration of that mole per decimetre cubed. So here, an example question. We want to know what mass of sodium carbonate is required to prepare 100 centimetres cubed of a 0.25 mole per decimetre cubed standard solution. So the very first thing we need to do is we need to work out how many moles are required. So how many moles? If we've got 100 centimetres cubed, we've got to do the concentration that's required times by the volume. And so we've got 0.25 times 100 centimetres cubed divided by 1,000 and equals 0.025 moles are needed. Now, we want to know how many grams of sodium carbonate this is. The next thing to do is to work out what the molar mass of sodium carbonate is. The relative atomic mass of sodium is 23, we've got 2 of those, then carbon is 12, and then oxygen is 16, of which we have 3. The total molar mass is 106 grams per mole. Now we use that formula, the one that I said was very important. The number of moles is equal to the sample mass divided by the molar mass. We want to know what the sample mass would be if we know the molar mass and we know the number of moles. The number of moles times the molar mass would give us the sample mass, and that's what we do, 0.025 times 106. That means we have to add 2.65 grams of sodium carbonate into this substance. Now, there is such a thing as a mass concentration, which rather than being interested in the number of moles per decimetre cubed, is interested in the mass per unit volume, or the grams per decimetre cubed, sometimes used if non-molecular substances are involved, or in industrial and laboratory processes. But a very important thing to consider here is the fact that if we've got the mass per unit volume, this is actually just a measurement of the density of the substance. We have spoken enough about liquids now. We want to now look at what happens with gases. And Amedeo Avogadro, he realized that 2 equal volumes of gas at the same temperature and pressure contains the same number of particles. Now, that means that 1 mole will always occupy the same volume, irrespective of what substance it is. And we call that volume the molar gas volume. It's the space that 1 mole will fill. The symbol for it is capital V with a subscript M. The unit is the volume per unit mole, and that would be measured in decimeters cubed per mole, or dm3 mole to the -1. At room temperature and pressure, this just so happens to be 24 decimeters cubed, or 24,000 centimeters cubed. And by room temperature and pressure, I mean a temperature of about 20 Celsius and a pressure of about 101 kilopascals. If 1 mole fits in 24 decimeters cubed, and I produce a volume that is different to this, I can actually work out what fraction of a mole I've got. If I filled 12 decimeters cubed of gas, I would know I've got half a mole. And if I had 6 decimeters cubed of gas, I would know I've got a quarter of a mole. Now, how we can relate this together formally is to actually work out that the amount of moles is equal to the ratio of whatever volume you've got divided by this molar gas volume. What fraction of that molar gas volume have you got? Because that is what fraction of a mole you have. Now, this works both in decimeters cubed, with the number of moles equaling the volume divided by 24, or alternatively in centimeters cubed, where the volume is divided by 24,000. You can always work out how many moles you have of this gas by comparing it to that molar gas volume and seeing what fraction of that molar gas volume you're working with, because that is what fraction of a mole you now have. When we have 1 mole, the pressure multiplied by the volume divided by the temperature equals something called the molar gas constant. It's basically a constant that enables these numbers to equal each other when we put them into this, the ideal gas equation. Now, this is making some assumptions. It's assuming that the particles are moving randomly in this gas, that they have elastic collisions, they have a negligible size with no intermolecular forces, etc., etc. Understanding this means that what we can do is work out key things about a gas. If we know how many moles it has and two more things such as the volume and the temperature, then we could work out the pressure. This formula is different from the previous ones because the molar gas constant has been calculated in the assumption that the volume was measured in meters cubed. It would be a different value of the molar gas constant if the volume was measured in decimeters cubed. So when we use this formula, what we need to do is make sure we're using the volume in meters cubed. So if it's in decimeters cubed, we have to divide it by 1,000. If it's in centimeters cubed, we have to divide it by 1,000,000 to process any questions using this formula. A typical question for this PV equals nRT, ideal gas equation, is to work out what the standard room temperature and pressure might be. They probably give you the pressure of the room, 101 kilopascals, which of course you would have to convert into pascals by timesing by 1,000, which would be 101,000 pascals. The volume of 1 mole of gas is 24 decimeters cubed. We need to convert that into meters cubed first by dividing by 1,000. And N is equal to the number of moles, which is 1. The molar gas constant is always equal to 8.31. What temperature produces a pressure of this much for 1 mole of gas? And the answer is 291.556 Kelvin, which my calculator tells me is about 18.5 degrees. So that's how you would use it to work out things like the room temperature and pressure, temperatures or pressures.